Hello, I'm Lou Bloomfield, and this is How Things Work. Today's topic, seesaws. Seesaws have been around for a very long time. They're one of the original playground toys for children. They consist really of a beam and a pivot that holds the beam's center and supports the beam's center. And the two children sit at opposite sides of the beam around that central pivot, and they can teeter back and forth very easily. Moreover, anybody who's played with seesaws has discovered that if you've got two children that are the same weight, they can sit at the same distance from the pivot, albeit on opposite sides, and teeter back and forth easily. But if you've got one big kid and one little kid, it's not so easy. How do you deal with this? Well, it turns out it still works, but the big kid has to sit closer to the pivot. And when that happens, you can balance the seesaw anyway, and the two can teeter back and forth. Well, how does all this work? And how do we describe these sorts of motions? To begin with, this teetering back and forth is rotational motion. The beam isn't going anywhere. It's not leaving and heading out of view. It's simply turning first one way and then the other. To make that clearer, let me take the children off the seesaw. Sorry, guys. And I'm going to pick the seesaw up. It's just sitting here. The pivot's just sitting there. And I'll hold it in something other than my hands so it's nice and slippery. And I'll give it a spin. There we go. The seesaw board can now obviously rotate. It's not going anywhere, it's rotating somewhere. And the other thing to notice is it has an inertia to it. If it's motionless, it tends to remain motionless. If it's rotating, it tends to remain rotating. In fact, about a fixed axis in space, as we'll see. And it rotates at a steady rate as well. Well, that leads us, and will lead us, in fact, to Newton's first law for rotational motion. But before we go to Newton's first law for rotational motion, let's develop some language with which to describe rotational motion. And in fact, I'm going to represent briefly 5 physical quantities that are analogous to the 5 physical quantities of what I'll now call translational motion. Up until now, I've talked about I have a position, I'm changing it, I have a velocity right now where my position is changing with time. Here's a different velocity, and an acceleration where I change my velocity. So here I'm heading to the left, now I'm slowing down, now I'm heading to the right. All described by acceleration there. And these are translational quantities. I'm moving in a type of motion that's called translation. Similarly, there's forces cause accelerations in the world of translational motion, and mass resists it. How about for rotational motion? For rotational motion, there are, again, 5 physical quantities. There's some subtleties to them, but I'll try to keep it simple. For rotation, there are quantities that describe orientation, how orientation is changing with time. The first such quantity we can call angular position, which tells you how an object is oriented at present. Mine, for example, how I am oriented, and therefore my angular position. To begin with, we need a reference orientation, what we'll call the zero of orientation. Just as we had a reference location for position, we have a reference orientation for angular position. This is it, 0. And if I orient differently, for example, this I have turned 90 degrees, we can call it, away from the reference orientation. So I would say this is 90 degrees, but that's not quite enough information. This is 90 degrees. This is 90 degrees. Uh-oh. And this is 90 degrees as well. There's an ambiguity here. In order to distinguish them, we need a direction. And the direction is not obvious, not intuitive necessarily. People thought about this long and hard. How do we identify a direction with this that's distinct from this, it's distinct from all the other possible 90 degrees? And the answer the convention is that we pick the direction along which a line, if you imagine there is a line going vertically right through me, a rotisserie axis, and you rotate me this way, and rotate me this way at 90 degrees, this we can say that my current orientation is 90 degrees along that vertical axis. We're not quite there yet, but this is the first step. So this is 90 degrees about a vertical axis. And that definitely distinguishes it from this one being 90 degrees. In this case, I'm being rotated about an axis that's going, here we go, whoop, rotate. 90 degrees about a horizontal axis pointing toward you and away from you. That's this, okay? So far, so good. We've almost pinned down my angular position now. There is still one ambiguity left. This is 90 degrees about a vertical axis, and this is also 90 degrees about a vertical axis. Two possibilities. And so to distinguish those two, we take advantage of the fact that a vertical axis has two directions along it. One of them straight up, one of them straight down. And by convention, this one is considered to be straight down. And this one is considered to be straight up. And you'll notice I'm pulling out my hand and playing finger games here. Why am I doing that? Because the convention is this. It involves your right hand. If you are left-handed, great, but you're going to have to use your right hand for this story. You take your right hand and you point your thumb. Mistake. You point your fingers in the direction in which you rotate. For example, like this. Here this is 0. Orientation 0. Ready? Rotate. I rotated, my fingers curved in the direction I rotated, and my thumb is pointing which way? Down. So I'm currently oriented 90 degrees away from orientation 0 in the downward direction. In this, the other possibility where I'm going to go this way, I take my hand, rotate, and look, my thumb is pointing up. Thumb of my right hand. This is 90 degrees up. Okay, so the bottom line in all this story is angular position has an amount and a direction. It's a vector quantity. The direction part, not so obvious and intuitive. You gotta think about it. It's very useful to physicists and engineers, maybe not so useful to ordinary folk, but it's worth seeing once. And the direction associated follows a right-hand rule. You make the rotation, and the direction of the rotation points along the rotation axis, which is the pivot, the rotisserie, and you use your right hand to figure out which direction along that rotisserie is involved. This is down, this is up. End of story. Okay, so angular position now, we can describe the seesaw's orientation relative to, say, this is 0. Fine, we're part of the way, but more interesting than its orientation at one instant in time is how that orientation is changing with time. Because when the kids teeter back and forth, it's actually rotating. It's changing its orientation. In that case, it has an angular velocity. So we have angular position. Angular velocity is the rate at which angular position is changing with time. In analogy to how velocity is how position changes with time. So angular velocity, how your orientation is changing with time. Let me develop an angular velocity other than 0. This is it. This is 0. My current angular velocity is 0. It's boring. I can talk to you like this all day, and probably already have. So if I want to have an angular velocity that's not 0, I have to do something that I'll come back to. I'll do it. Okay, now I've got it. Here's my angular velocity. You can see it. My orientation, my angular position is changing with time. And how do we describe this angular velocity? Well, it's about 90 degrees every second. That is, I'm here, I'm here, I'm here. About 90 degrees every second. And that's already pretty good. You know a lot about my angular velocity, but you don't know, am I doing this? Or am I doing this? You know, and obviously I can't keep doing it. Or other possible axes of rotation. So we need a direction to it too. So this is 90 degrees along a vertical axis, because that's the rotisserie. And furthermore, following the right-hand rule, I am rotating, here's my fingers, I am rotating about the upward direction. My thumb is pointing upward. This is 90 degrees per second upward. Let me get a different one. This is 90 degrees per second downward. So that's angular velocity. So we can now begin to describe how this thing is rotating. I can't rotate it very far before it hits something, but for a brief instant there, it was rotating a few degrees per second about an axis away from you. All right. Last thing to do is we're gonna have influences that affect rotation, and they're going to be analogous to forces, but they're not forces. Forces cause things to translate, to begin to move, in fact, to accelerate, to change their velocity. These are things that cause, the influence that I have in mind now are ones that cause rotation to change. In particular, to cause an object's angular velocity to change with time. And those influences are called torques, T-O-R-Q-U-E. The word torque doesn't show up very often in everyday life, but it shows up in things like the specifications for an engine or a car turning its wheels, or in the specification for wrenches trying to tighten or loosen bolts. So, with the concept of the influences known as torques and angular position, angular velocity, I can now state Newton's first law for rotational motion. And that is the following. And I'll say it in its full glory, and then I'm going to have to tell you about a couple of the words that are thrown in and seem like, where did those come from? And what Newton's first law of rotational motion says is that a rigid object that is not wobbling and that is not experiencing any outside torques moves at constant angular velocity. So it sounds a lot like Newton's first law of translational motion. I mean, I have to give this thing little twists occasionally in order to keep it going because of frictional effects. Furthermore, I should say, when I say give it little pushes, little torques, what is a torque? You know, I said I'm going to come back to Newton's first law. Don't worry. That I said that that the influences known as torques cause changes in angular velocity. As we'll see, they cause angular acceleration. But a torque, you know, what is it in everyday life? It's a twist. So if I want to get this thing spinning, let me pull it out here. If I want to get this thing spinning differently, right now it's not spinning at all. I want to get it to spin differently. I twist it. Twist. So that act of twisting, like you do to the lid of a jar, or to the crank on your bicycle pedals, that is a torque. Okay, so that said then, an object that's free, a rigid object that is free of outside torques, turns at constant angular velocity. It also has to not be wobbling. What's the rigid and the not wobbling business? Well, if the object can change shape, as a person can when they've dived off a diving board, then Newton's first law for rotational motion doesn't apply anymore, because they're not rigid, they're changing shape. That messes the law up. It just simply says that you don't obey the law, because you're violating one of its expectations. The other thing is that Newton's first law does not describe wobbling objects. A wobbling object is one that is rotating in effect in a couple of different ways. I can make this guy wobble and it'll be disastrous. I'll probably get skewered. But you've seen things. I'm not going to throw up that and get it to wobble. Do I have anything here to have it wobble? Nah, good enough. So wobbling objects, things that are sort of going every which way as they spin around, also not included, not described by Newton's first law of rotational motion. So rigid objects, ones that are not wobbling, they coast. They coast rotationally. Simple as that. All right. What about the effects of torque? Well, if you exert a torque on an object, and in fact the object's experiencing only that torque affects the object's rotation, angular velocity. It causes the angular velocity to change with time. So let me exert a torque on this. I'll come back over to it like this and give it a torque, twist, and suddenly it has a different angular velocity. During that period of time, and I did it again to stop it, during that period of time when I was exerting a torque on the seesaw board here, it was undergoing angular acceleration. Its angular acceleration is the rate at which angular velocity changes with time, and I was causing angular acceleration. So I can illustrate that myself. I can undergo angular acceleration. To do this, I need to get a torque. A torque has to be exerted on me. What's going to exert a torque on me? The ground. I'm going to get the ground to twist on me. Because I'm going to twist on it, it's going to twist back. There's instantly a Newton's third law for torques, for rotational motion. Newton's third law for rotational motion says that if you exert a torque on one thing, that thing exerts a torque back on you, equally strong in the opposite direction. Torques, after all, have a direction. If I twist you that way, which from your point of view is counterclockwise, that's different from me twisting you clockwise. So torques have a direction. They follow a right-hand rule too. A torque like this is toward you, and a torque like this is away from you. So torque is another vector quantity. And if I exert a torque on the seesaw board that's toward you, the seesaw board exerts a torque on me that's away from you. And those two torques are equal in amount in opposite direction. They never cancel because one torque, my torque on the board, affects the board, and the other torque, the torque the board exerts on me, affects me. So they have to be equal and opposite. There's never any point to summing them to zero because that's boring. They don't affect the same object. But Newton's third law appears for rotation as well as for translation. So we've got a seesaw board here. If you twist it, its angular velocity will change with time. It will undergo angular acceleration. If you twist this board, you have an effect on it. Alternatively, if I twist this little stick, I'll have an effect on it that's much more severe. The same twist, as in the same torque on this little guy, has a much bigger effect on its angular velocity than the same twist on this big guy. How do we describe that? This big guy has more rotational inertia than the little one. How do we describe that? Well, we characterize this as a rotational mass, as a rotational resistance to angular acceleration. And this board has a larger rotational mass than this little stick. It's not too surprising. There is then a Newton's second law for rotational motion, which is analogous to Newton's second law for translational motion. And what it says basically is that if you take an object that has a certain rotational mass and you exert a certain torque on it, it will undergo angular acceleration. And the angular acceleration it undergoes is going to be equal to the torque on it, particularly the net torques. We're going to assume that you control all the torque. So the net torque divided by the rotational mass. And that describes how the object undergoes angular acceleration. Okay, so we've got a seesaw board. You can teeter back and forth about a pivot, and we can exert torques on it and cause it to undergo angular acceleration, and the angular acceleration are controlled to some extent by how much rotational mass this thing has. Before I go much further, let me just take a moment to think about that pivot. What's the point of the pivot? Why do I have it there? You know, it's stuck through there, it's sitting on those two blocks. Why? Well, if we don't have the pivot, this overall object is going to fall because it's not going to be supported, right? Ready, get set, it falls. So the pivot stops translational motion that naturally would occur, in fact, by sort of canceling any forces on the overall board and allowing it to just exhibit pure rotational motion. Well, that brings us to the idea that is translational motion completely separate and different from rotational motion? And can an object do one or the other or both? Or how does it all work? Yeah, rotational motion can be described in terms of translational motion of all the little parts. So this thing is moving up faster and faster, and then so on. You can describe rotational motion using translational motion. So rotational motion isn't essential to the world of physics or anything else. You can describe everything associated with rotational motion using translational quantities of all the parts. Similarly, you can do the opposite. You can describe translational motion in terms of rotational motion of all the parts. It's too hard. There are times when you just want to use translational motion stuff, like when you're walking, taking the dog for a walk, okay? And there are some times when you want to describe the situation strictly with rotational quantities, like when you're playing Seesaw. And then there are some times when you want to do both. You want to have some of both, like when you throw, I'm doing it with a glass bottle, really clever choice here. Woo! Okay, when the bottle is going up and spinning at the same time. Whew, I survived that little trick. Interestingly, it's doing two things at once, and we can use both translational motion and rotational motion to describe it. It is, on one hand, it is traveling in some sort of arc. I don't want to do this too many times. Woo! I didn't want to do it anymore. It's traveling in some arc like this, and that arc looks a lot like the arc of a falling ball. In fact, it is the arc of a falling ball if we watch one special point in the bottle. That special point is the point at which the mass of the bottle is all sort of balanced around it, centered. There is what's called the center of mass of an object. In this case, it's in the middle of the bottle. And that's the point of the bottle that we can treat as though the whole bottle is there. And that one spot travels in the lovely arc of a falling object. In this case, thrown at an angle, it travels in a parabolic arc. So watch the center mass, that's what happens. At the same time, however, the bottle is spinning, because it's a rigid object, it wasn't wobbling, it's following Newton's first law of rotational motion. It's spinning at constant angular velocity. About what? About its center of mass. The center of mass is that special point then about which the mass is balanced. It's the natural pivot for an object. So if I spin the bottle is spinning about its center of mass. In this case, because I'm supporting it, the center of mass sort of stays put. If I stop supporting it, throws it, the center of mass falls. It travels in the arc of a falling ball. So you can have situations where you have translational motion only, walking the dog. You can have situations with rotational motion only, seesaws. And you can have motion where both are taking place together, and that's a tossed baton or tossed ball or bottle or whatever you want to throw, beach ball. Okay, so we're back to seesaws, and seesaws exhibit this rotational motion. What about putting the kids on them? When you put the kids on them, and I'll put one kid on first, it clearly the kid produced some sort of rotational motion in the board. It underwent angular acceleration toward you and went from being horizontal to being tipped so the bottom, we're losing stuff, tipped so that the kid is low. How did that happen? The kid has a weight, which is a force, and yet it produced a torque on the board. It twisted the board. How does that work? Well, it turns out that just as rotational motion and translation motion are not completely separate from one another, you can just use one to describe the other and vice versa. Forces and torques aren't completely separate from one another. The torque that this kid exerted on the seesaw is produced by a force. The kid is sitting on it and using the fact that the kid has a weight to push down on that part of the board. What are the rules for this? You're producing a torque with a force. How does this work? This is the world of levers. The answer to this is that when the kid pushes down on this spot on the board, and now having lost some of the balancing parts of this board, let me put them back on so I get it back. Yeah, old tape. The board is no longer perfectly balanced. I'll use fresh tape to fix it. How things really work. You have to fix them from time to time. Problem solved. Instead, I was putting extra weight on this side of the board since it's a little short. Where I put the pivot isn't quite right, and so I needed to add a little bit of extra weight there, as though there were a little kid on there producing a little extra torque on that side. Okay, well, we can come back to that or not, but the point is that I'm trying to deal with right now is the kid, by virtue of having a weight and the ability to push down on the board, pushes down on this side of the board and causes angular acceleration. How did that happen? The kid produces torque, and the rules for the torque that you produce are this, that you go away from the pivot. So if I push on the pivot, put the kid on the pivot, boring, nothing happens. Well, I mean, gotta get the kid right dead center on the pivot. Okay, nothing. Go away from the pivot to a distance, and then push. And don't push it any old direction. You don't want to push toward the pivot or away from the pivot. You want to push at right angles to the pivot, or something like right angles to the direction of the pivot. So you come out a distance and push at right angles to that distance you travel. Well, it's not really a distance you travel, it's a vector. This vector from the pivot to where you push, that is, it's got a distance and a direction. So it's a vector. Sorry about that. That's the way it is. That vector has got a name. It's called the lever arm. So you come out to the lever arm and you push at right angles to the lever arm. You produce a torque. Whoa! Good as that. The torque that you produce has a direction, because torques do. The direction follows another right-hand rule. You have your index finger follow the lever arm, and your third finger point in the direction of the force, and your thumb points in the direction of the torque that produces. So a kid pushing out here produces a torque toward you. A kid coming out here and pushing down here produces lever arm, push, a torque away from you. And that's how two kids on opposite sides can cancel one another's torques. They can make it so that together they exert no torque on the seesaw. I should say at this point that the amount of torque that each force produces is the product of how long that lever arm is times how strong the force is. And there's some angle stuff in here if you're not perfectly at right angles. Assuming right angles perfectly, then it's just the length of the lever arm and the strength of the force. Done. So this might be, this can, I don't know, what does it weigh? 5 newtons maybe, and we're out here at maybe half a meter. So this is 5 newtons times half a meter. That's 2.5 newton meters, which are the units of torque. So this is 2.5 newton meters toward you, and this is 2.5 newton meters away from you. We add them as we need to do to see about angular acceleration. What's the net torque? It's 0. This one's pointing toward you, that one's away from you. They're equal in amount. They cancel. Nothing. So that's what happens when two kids are playing seesaw and they properly arrange it so that the seesaw doesn't undergo angular acceleration. They have balanced the seesaw, and that's what balancing means. Balancing means having it so that it's experiencing zero net torque. In particular, in this case, it's zero net torque due to gravity. The weight of the kids is responsible for their ability to push down. And so there's no, if I get it right, there's no torque due to gravity on this board right about there, and it is balanced. If you don't have two big kids, you got a little kid, you put the little kid out far to give them a long lever arm because they're not going to push very hard. Big lever arm, little force can balance little lever arm, big force. That's how the balancing works in a seesaw. You try to make it so that the two kids together, whatever their sizes are, manage to exert zero net torque on the board so that it undergoes no angular acceleration or angular acceleration zero. And you do that by adjusting the lever arms of the two kids. All right. One other way to look at this situation is, at this point, gravity is exerting no net torque. There's no net torque on the board due to gravity. The overall weight of this board can actually be considered to be located at a single point. If you take into account that this a little weight out here, there's a lot of weight in here, and so if you add up all the little pieces of weight, considering where they're located, you can arrive at one point at which the seesaw's effective weight is located. Where if you have to distill down gravity's force on this entire board, at what point does that gravity act? And in this case, it acts right there. That's the point. It's under my finger. I can't touch it. It's inside the board. That's the effective location of the weight of the whole board with the kids on it right now. And that is what's known as the center of gravity of the board, the effective location of its overall weight for this, when you have to simplify the problem. And so by putting the center of gravity right on the pivot, gravity cannot exert any torque on the pivot. There's no lever arm to work with. If you shift things, however, so the effective weight of the board is way out here to the right, you put both kids on one side. Now the center of gravity of this board is not on the pivot anymore. It's somewhere around here. That's where you would simplify the world down and say that's where gravity is acting, center of gravity. It's quite distant from the pivot. So there's a lever arm that for it, and it acts down here, down at right angles. So it's exerting a torque on this. In the absence of the table to keep it there, the kids would be on the floor. All right, so that's the seesaw balanced is like this. And one last thing to look at as we do this, or two last things actually. First, as the kids rock back and forth, which they do by unbalancing the seesaw, either by leaning or by putting their feet down so they get extra forces and therefore produce extra torques. The closer the kids sit to the pivot, the more easily it rocks back and forth. Right now, this board has a huge rotational mass because when it rocks back and forth, not only is the board rocking back and forth and having to undergo angular acceleration, but the kids are too. And they're way out there where they contribute a lot to the rotational mass of this overall object. This is hard to twist back and forth. If you're the third kid and come in here and go, let's twist the board back and forth, it's tough. But if you bring the kids in close so that their masses are close to the center, this board now is a lot easier to twist back and forth. So, in looking at rotational mass, an object's rotational mass is not completely unrelated to its mass. Rotational mass is derived from the mass and how that mass is located. And it turns out that the farther the mass pieces of the object are from the pivot, from whatever you're twisting it about, the center about which you're twisting it, the farther those mass pieces are, the more they contribute to rotational mass. And it's a dramatic effect. Moving this kid from this distance to this distance, that is twice as far from the pivot I have in mind, increases that kid's contribution to rotational mass, not by a factor of 2, not by just simply by the fact that I'm double its distance. It increases it by a factor of 4. The contribution goes as the square of the distance. So this is a big effect. Put the kids out far, woo, huge rotational mass. Bring them in, very small rotational mass, easy to rock back and forth. Okay, and that affects certain situations where why does a tightrope walker have a long stick maybe to help balance with? Because by putting a lot of mass in that stick way far from the pivot, that stick develops a huge rotational mass, and it's very hard to make it undergo angular acceleration. So if you twist it, it doesn't change much, but it twists back on you and gets you back on top of the rope. So helpful hints next time you're tightrope walking. Last thing I want to talk about, and then I will leave the story, is let's watch the two kids as they rock back and forth. As this kid, I'm trying to get balance again. Okay, as the purple kid over here descends, the purple kid is losing gravitational potential energy. It's going from high to low. The gravitational potential energy is vanishing from the kid. Where does it go? It goes into the red kid over here. The red kid was lifted up. So as the red kid descends, the red kid's energy goes to purple. So energy is going back and forth as these two kids rock back and forth. They're moving the energy back and forth. And if we change out one of the big kids for a little kid, well, of course, we got to get it to balance, we have to go back, bring the big kid in close. So now, as they rock back and forth, the big kid with a lot of weight is going up and down a short distance. So the change in energy, gravitational, between this position and this involves a big force for a little distance, which gives you a certain amount of energy. At the same time, the other kid is moving in the opposite direction and is going from way down low to way up high. That's a big distance traveled with a small weight. The energy associated with that, the force times the distance, is the same. So this kid, the red kid as it descends, ultimately does work on the little guy as he rises or she rises, and the energy is perfectly transferred between them. The energy that one kid loses, the other kid gains, and back and forth and back and forth. So seesaw is another viewed perhaps only in a way that physicists would like or love, is the energy is going back and forth between the two kids as they teeter back and forth. And with that, I'll end the story of Seesaws.